Hello, it's Justice here. Welcome back to my YouTube channel. Today we're going to be solving Leetcode question 802, find eventual safe states. So there is a directed graph of n nodes with each node labeled from 0 to 1. And the graph is represented by a zero index 2D integer array graph where graph I is an integer array of nodes adjacent to node I. That means that there is an edge from node I to each node in the graph I. So a node is a terminal node if there are no outgoing edges, and a node is a safe node if every possible path starting from that node leads to a terminal node. And we can count terminal nodes as safe nodes. So they want us to return an array consisting of all the safe nodes in the graph, and they just want that to be done in ascending order. Okay, so we can say here, we can look at how this graph is constructed. Through this example, we can see that the node 0 here has edges that point to node 1 and 2. Node 1 here has edges that point to 2 and 3. Node 2 has edges that points to node 5, etc. We can also see that 5 and 6 are going to be both our terminal nodes because we see it has no edges that it's connected to. So this path leads to nowhere. Once we get to 5, there's no other place that we can go to. So how do we know that a node will never be a safe node? So we know a node is not a safe node. We know that a node is a safe node if every possible path starting from that node leads to a terminal node. So if we lead to a terminal node, we know that there is no other place to go to because terminal nodes have no other edges to go to. So that path is not going to have any revisited nodes. So if we can take a look at the example here, at one of the examples here, we can see this example. If we start at 0 and go to 2, that points to 2. And then this 2 points to a terminal node of 5 here. So we can see this possible path is a good path because this leads to a terminal node. And as you can see, we've never revisited any characters because once we hit a terminal node, there's no other place to go. So there's no other way for us to revisit. So if we take that into consideration, we know that a path is not going to be a good path if we're revisiting nodes multiple times in our path. So let's say we chose this path, for example, from 0 to 1 here. And then we chose a path from 1 to 3 here. And then from 3, the only place we can go is 0. So as you can see, we're going to hit a loop because we already started at node 0 and then we're actually coming back to node 0 in this loop. So there is no possible way ever for this to flow to any of these terminal nodes. So if you think of it as water flowing down a river, once we hit the bottom, there's no way for the water to go back up. But if we ever hit a path where the water circles, it's never going to be able to hit the bottom. So in this loop, if the water actually hits a loop, it's never going to actually get to a terminal node. So we're going to use that intuition in a way to solve our problem and kind of write that out and check for all the possible paths. Okay, let's walk through this graph and check the node and each one of their possible paths by keeping track of which nodes we've been visiting. And if we ever find a path in which we visit a same node twice, then we know that that node that we're looking for the path in is not a safe node. So we're gonna start at node 0 here and we're gonna delineate this as visiting, and we're gonna say it's visiting because we have the kind of orange coloring on it, and we're going to go through all its edges. So node 0 has a path to 1 here, and node 0 also has an edge to 2. Okay, so we're going to also mark node 1 as visited, and we're going to mark node 2 as visited. Okay, so now we're going to check all of node 1's neighbors. So node 1 has a neighbor or an edge called number 2 to node 2, and then also to node 3. So we can say node 2 is visited and also node 3 is visited here. Okay, cool. And then we're going to say, okay, so for node 2, we're going to check all of node 2's neighbors. Node 2 only has one neighbor, and that points to node 5. And remember, node 5 is a terminal node because node 5 has no other edges that it points to. So there's no way to hit a loop once we get to a terminal node. So we know that that node 2 points to a safe node here. So in conjunction, we also know that node 6 here is a safe node too, because it also has no edges. But since node 2, all of node 2's edges, which is only one edge, points to a terminal node, we know that node 2 is a safe node because every single possible path from this node here, from node 2, leads to a terminal node because it only has one path that leads directly to node 5. So we can delineate node 2 here to being a safe node. And we're going to say that safe nodes are going to be shown in green. So we say node 2 here is a safe node. Okay. Now let's take a look again. So we already seen 1 from its neighbor 2, and now we're going to see node 1 from its neighbor 3 here. So we go to node 1, which is second neighbor, which is node 3, and we're going to say, okay, what are the neighbors for node 3? So neighbor has a node 3 or an edge that points to node 0. But as you can see here, node 0 has already been visited, and you can see that we've also went through a loop because we started at 0, we went to 1, and then from 1 we went to 3, and then from 3 we went back to 0. So since this is in a loop and we're back to a node that we already visited, we know that 3 is definitely not a safe node because it points to a node that is already visited. So we're going to take that out, and we're going to delineate node 3 as not being a safe node. So this is not a safe node, so it's going to be in red. So we know that 3 is not going to be in our results. And then also we also know in case 2, this node 1 also points to a node that is within a loop. So we know that 1 is also not a safe node because there's a possible path from 1 that will never reach a terminal node and it will be stuck in this loop. So we can say 1 as well. This node 1 is also not going to be part of our solution, and this is not a safe node. Okay. And then same thing for this node 0 here. This was included in the loop, so every node that is included in that loop is not a safe node because from there we have a possible path that will be stuck in that loop and will never reach the terminal node. So we can say this node 0 here is also not going to be part of our solution. Okay, so we know that node 0, 1, and 3 are definitely not safe nodes. We know that 2 is a safe node. So now let's check 4. Okay, so we're going to mark 4 as being visited because we're going to start at 4 here. And we're going to check 4 with all its possible edges. So we see 4 only has one edge that points to node 5, and we know that node 5 is a terminal node, so it is another safe node. So in conjunction to that, all the possible nodes from node 4 have a possible path going to a terminal node. So we know that node 4 is also going to be a safe node. So we're going to delineate that as a safe node, and 4 is a safe node here. So that is kind of how the output has been computed, and we're going to make sure that that's in ascending order. And since we did the graph traversal here in order because it's labeled from 0 to n-1, we actually can just update the results kind of like that, and that's kind of how our result is going to be. So it's going to be 2, 4, 5, 6 as being the safe nodes, and we're going to make sure that we don't include any of the nodes that are not safe or any of the nodes that are included within a loop to not be in our solution. So we're going to go to the code and code this one up, and I can show you how to do this most optimally in code by keeping track of the states that we're currently in. Okay, so now let's write the code. So first we're going to start with n equal the length of the graph because we're going to be traversing through the whole length of the graph, and we don't want to be writing this over and over. And then we're going to have a state variable. But the states, we're going to say, let's start with 0 being a node that's unvisited. So if it's 0, that means that the node has been unvisited. If it's going to be 1, we know that the node is visited. And then let's say 2 delineates a node that's safe. Okay, cool. So now let's create a state array. We're going to initialize it to 0 for all the nodes in the length of the graph, because we haven't visited anything yet when we first walk through this. And then let's create a depth first search function on each of the nodes. Okay, so we know if we actually land on a node that has already been visited previously, we can return false. So if the state of the node equals 1, we know that we're back at a node that we've already visited, so we can just return false here. Otherwise, if the state of the node is 2, we know that we've landed at a safe node, so we can return true. Perfect. Otherwise, that means that this node is unvisited, so we can state of node equals 1. We can mark it as visited and then check all the node's edges or neighbors. For edge in graph node, so we're going to check all the edges for that specific node, and we're going to say if we traverse through all the edges and we find a path that returns false, so if we find a path that has a loop in it, we're going to return false. So if DFS of the edge, if not DFS of edge, we're going to return false. Otherwise, we've traversed through all the edges of that node and we've not found any loops, and we've also ended up at one of our safe nodes. So we know that all possible paths lead to the safe node, so we can delineate this node as being a safe node, and we can return true. Okay, so now we're going to return all the nodes in our graph I. And when we go through our graph, if the depth first search of that node returns true, and that's going to be returned in sorted order. Okay, so that's accepted. And that's actually pretty fast. So let's go for the time and space complexity on this one. So time is going to be O of V plus E. V plus E delineating, V delineates the nodes and E delineates the edges, because we're going through all the possible nodes and edges in our graph. And then for space complexity, we have that state array up here, and this state array is going to hold at most all of the nodes within our graph. So it's going to be O of V, where V is the amount of nodes in our graph. So we're going to be doing Leetcode daily problems for the first 100 days of the year on this channel. So keep in tuned, and I hope you subscribe to the channel, and I hope you learn something in this video. I'll see you next time.